Welcome to 2D kinematics, projectile motion. When you throw a ball through the air, the path the ball takes is very similar from math class. It is a parabola. Now this is assuming there's no air resistance. If there was air resistance, then it would end up falling a little bit short. And so the projectile, it wouldn't be completely symmetric, but for today's lesson, we are assuming that there's no air resistance, and so it's a perfect parabola. Under the effect of a constant acceleration due to gravity, it is clear why the motion would be modeled by a parabola. In math class, you likely have seen the equation of a parabola. It's in the form of y is equal to ax squared plus bx plus c. Consider the equation of kinematics. Here we have delta d is equal to v1 delta t plus 1/2 a delta t squared. So if you rearranged it, you could see that if you subtracted delta d from both sides, and this would be our first term, our ax squared. This would be our second term, our bx. And this would be our third term, which would be c. Rearranged and breaking the displacement into the difference between the final and initial positions, we have y is equal to ax squared plus bx plus c. Similar to how y is a second-degree function of x in the first equation, the final position is a second-degree function of time for an object experiencing constant acceleration due to gravity. In physics, we prefer to use overall displacement instead of initial and final position. But the rearranged version of the kinematics equation helps us to see the similarities between the equations. We have already looked at the motion of objects in free fall. Now we will add an initial horizontal velocity. Now the object is not falling straight down towards the ground, but has a parabolic curve. The shape of the curve changes depending on the initial velocity of the projectile. So now instead of just throwing something straight up and it falling down, it has a sideways velocity. So as it goes up, it's also moving to the right, and as it falls down, it's also moving to the right. If you were to throw a football, the path changes depending on the initial speed and the angle at which it was launched. All of these paths are modeled by parabolas with different coefficients. In fact, if you were to drop an object and launch an identical object horizontally from the same height, their motions are extremely similar. So here, you can see that if you were to just drop an object from here, and these are like, moments in time, like maybe every second or every tenth of a second. And you can see that because it's accelerating, the distance for every second or tenth of a second, the distance between the balls, if you will, increase. Okay. Now, if you look at the one over here, and I'll use a different color highlighter. If you look at this one, this highlighter isn't going to show very well. If you look at this one over here, you can see that the y values, the up-down values, end up staying the same. Like you can see that this lines up with this, and this lines up with this, and this lines up with this. Oopsie, I didn't draw that very well. This lines up with this, and this lines up with this. So if you look at those things, you can see that the acceleration due to gravity affects the balls the same way, even though this one over here has a horizontal velocity. And if you had another ball that was thrown with a bigger horizontal velocity, it would be similar. It's just that the path would be even wider, and yada, yada, yada. The ball launched horizontally travels the same horizontal distance in equal time periods. Yeah, so you can see that this, for every 0.1 of a second, the delta x distance is the same. The two objects' vertical positions are the same throughout the motion. The horizontal distance the second object travels is the same in equal amounts of time. Each second, the object's vertical velocity vectors grow longer because of the acceleration due to gravity. So the variables for projectile motion, there's a whole slew of variables. Let's label our diagram with all of the variables we could possibly think of. So here, if we have a ball that's thrown from the ground, like a football, you can look at it at different moments in time. So if we look at it at this moment in time, you can see at that exact moment in time, it's, the velocity vector is the tangent to that curve, which is that now purple line. It was red, now it's purple. And so you can break that resultant vector at that moment in time into its horizontal and vertical components. And so you can see here's the horizontal component, and then here's the vertical component. And so now you have, for time equals 0, you have a Vx and a Vy. Now the V1y is, now here you have your sine theta. So the V1y, if you think about this, this is SOHCAHTOA, right? And so sine of theta is equal to opposite over hypotenuse, okay? If this is our V1 and we're looking for the opposite, this is the opposite over here. So our V1y, we could erase this and say this is V1y. We could erase this and say this is V1, put the little hats on it. And so if you were to solve for V1y, you would multiply both sides by V1, and you would end up with this equation right here, which is V1y is equal to V1 sine theta. Okay. We could do the same thing for Vx, but notice because our horizontal is staying the same, we're assuming no air resistance, we can keep the same variable for every step. The horizontal velocity is going to stay the same the whole way. Okay. Theta is the launch angle. V1x is equal to V2x, which is equal to Vx, which is equal to V1 cosine theta. And again, over here, we could have this Vx, this is the adjacent, and so we have cosine of theta is equal to adjacent over hypotenuse. Our adjacent is going to be our V1x, or Vx. We can just say, we can change, since they're all the same, we can just call this Vx, and our hypotenuse is just going to be V1. Okay. The maximum height occurs at half the time and half the range, right? The range is delta dx, maximum height is delta d1, and then the final velocity, it's going to be similar over here in that you have v2, this over here, and it should be very similar to our initial, but in the opposite direction. Okay, down instead of up, that is. Variables of projectile motion. Okay, so delta dx is the range, how far the projectile travels. Vx is the horizontal velocity. Delta t is the elapsed time. Delta dy is the vertical displacement, or the greatest at max height. 0 is what it is at the end, at the bottom. The horizontal variables, we have delta dx is the range, Vx is the horizontal velocity, and the time. And the vertical variables, we have V1y, V2y, right? These. Continue with the horizontal variables. We have the range, Vx, delta d, and in the vertical, you have the acceleration due to gravity, which is negative 9.8 meters per second squared, and the elapsed time. Finding the components of initial velocity. Many projectile motion problems provide the initial velocity of the projectile and the angle at which it was launched. Breaking initial velocity into horizontal and vertical components is a necessary step towards solving for the unknown values in each situation. the initial velocity must be broken into horizontal and vertical components because different equations are used for the horizontal variables and the vertical variables. So when you're dealing with two-dimensional problems, you oftentimes need to look at what's going on, like ignore the y stuff and just look at the x stuff by itself. And then you do the same for the y stuff, is you ignore the x stuff and you just look at the y stuff and you formulate your equations in the x direction and in the y direction separately, and then figure out how to solve. Horizontally, there's no acceleration. Therefore, there's only a constant velocity equation can be used for the horizontal variables. Vertically, there is a constant acceleration, so any of the 5 equations of kinematics can be used. To find the horizontal and vertical components of the initial velocity, you first draw the initial velocity vector with its magnitude and angle, create a right-angled triangle with the initial velocity as the hypotenuse. Label the horizontal velocity, and then use your trigonometric ratios to determine the magnitudes of the horizontal and vertical components. We kind of did it already, but here's another example. Determine the horizontal and vertical components of the initial velocity vector below. So pause the video and try to solve this on your own. Okay, so here, I'm going to change this to a different color. We have our initial velocity is 4.2 meters per second, okay? And so something is launched at this angle, and we know that that's the direction it's going to go. But we're going to break it into its x and y components. Okay, so here's the x component, here's the y component. And since it's the initial velocity, we could say that this is v1x, but we've already said that we are assuming that there's no air resistance. If there's no air resistance, then all of the horizontal velocity vectors should be the same. So you can just label them all Vx. Okay, since our theta is 54, using trigonometric functions, we know that cosine of theta is going to be adjacent, which is our Vx, over hypotenuse, which is our V1. Okay, if we rearrange this, we multiply both sides by V1. These cancel, and you're left with Vx is equal to V1 cosine theta. Similarly, we can do the same thing for V1y. You can say sine of theta is equal to our opposite, which is our V1y, over hypotenuse, which is our V1. So if you arrange that, that must be on the next page. So on this one, we can substitute in the values. So for V1, we have 14.2, and for theta, we have 54. If you plug that into your calculator, you should get 8.35 meters per second. Okay, so now doing the opposite, like here we were doing this. If we multiply both sides by V1, these cancel, and you end up with this equation right here. V1y is equal to V1 sine theta. You plug in the values, 14.2 and 54. And if you solve that, you get 11.49 meters per second. And this, if we look at, say, oh, does this make sense? We could say, yeah, this makes sense because we know that the V1y is going to be larger than the Vx, and it is. And we know that both the components are going to be smaller than the hypotenuse. So yes, our calculations so far seem to make sense. Any questions?